2 billion tons of waste are produced by humans every single year. Glass makes up nearly 20% of this global mass. One can notice how discarded bottles accumulate in landfills, where a single unit persists for over 1 million years without breaking down. But this is just the beginning. Why is this durability actually an industrial advantage? It seems counterintuitive for waste management, because glass can be recycled forever without ever losing its original quality. At first glance, broken shards appear to be useless debris, but in reality, they are ready for infinite reuse. Hundreds of tons of material arrive daily at one of the world's largest recycling factories. The raw glass moves toward machines that will turn messy fragments into clean, shiny bottles. It gets more complex further on. The unbelievable journey of sustainable recovery is now underway. 10 to 20 cents? This is the precise value assigned to a single empty glass bottle in many European countries. Why is such a specific price tag attached to what appears to be garbage? At first glance, tossing an empty soda container into general waste seems like a convenient disposal method. But in reality, this mixes glass with household refuse, making the subsequent sorting process prohibitively expensive and technically difficult. To handle this problem right at the source, automated return machines are installed across city streets. Consumers simply place an empty bottle into the intake, and one can notice how the device immediately scans and sorts it. A small refund is issued, meaning a freshly finished beer bottle transforms from waste into a valuable asset with cash value. This approach motivates people to collect bottles on their own, providing factories with a stream of glass that is pre-sorted, clean, and consistent. But this is just the beginning of the logistical journey. When the reverse vending machines are full, collection companies deploy specialized trucks to pick up the accumulated glass. Forklifts lift large plastic bins, each holding thousands of empty bottles, onto the cargo beds. A single full-size truck can carry between 20,000 and 30,000 bottles in one trip, equal to about 10 to 12 tons of material. Trucks loaded with these tens of thousands of empties make their way from supermarkets directly to the recycling plant. Upon arrival, the drivers back up to a massive storage bay and release the load, sending a cascade of bottles tumbling down. In just minutes, the ground fills with colorful mountains of glass that sparkle under the industrial light. Greens, browns, and clears stack together in giant heaps. These piles are not just waste. They are the starting point of the entire recycling chain. A steady supply of raw material now lies ready to be cleaned and crushed. Tens of tons of waste glass tower in chaotic piles, awaiting their turn for transformation in the recycling yard. Massive loaders drive up to the mounds, their engines straining as they scoop up huge loads with reinforced buckets to carry across the facility. With a thunderous crash that echoes through the site, the glass is finally dumped into the plant's feed hopper, sending a sharp cascade of shards sliding down the steel chute. This aggressive start launches the material into the recycling cycle, but the path to purity is long. The steel conveyor immediately starts moving, carrying the jagged stream of glass, still heavily mixed with dirt and sand, deep into the heart of the facility for processing. At first glance, the vibrating screen looks like a simple sieve, but it performs a critical separation. Powerful mechanical shakes dislodge and filter out dust, grit, and tiny particles that would otherwise contaminate the melt. One can notice how the fine debris falls away, leaving the main glass flow significantly cleaner. However, larger contaminants that machines cannot easily detect still remain in the stream. Along the conveyor belt, human oversight comes into play. Workers stand ready at the line, their eyes scanning the moving belt to carefully pull out paper, plastics, and any other foreign objects that do not belong. This blend of mechanical screening and manual precision produces a much cleaner batch of material, ready for the next step in the recycling journey. It gets more complex further on. Do you know what is still hiding in that moving pile of broken glass? To the naked eye, the flow seems to consist only of transparent shards, but the bottle caps are often made of metal, posing a severe threat to the furnace. Fortunately, a high-powered magnetic separator solves this problem effortlessly. The principle is simple yet effective. A strong magnetic field grabs the bits of steel and lifts them away, while the non-magnetic glass keeps moving down the conveyor undisturbed. Thanks to this step, the raw material is now about 80% clean and one step closer to its journey of rebirth. The glass moves on to the next crucial step, being ground into cullet within a hammer mill. A massive machine with high-speed rotating hammers smashes the glass over and over until only tiny fragments remain. Any pieces that are still too big are automatically detected and sent back through the mill until they reach the right size. This ensures the entire glass stream becomes uniform, with no stragglers slipping through the cracks. The process creates cullet, fine, sparkling glass particles that look almost like man-made sand. Because it is broken down so small, cullet melts much faster in the furnace, saving up to 40% of the energy compared to using raw materials like sand or limestone. And this is not the limit. One can notice how the cullet enters a powerful suction system, where a strong stream of air strips away and blows off any leftover label fragments, leaving the glass even cleaner. Optical sorting represents the most precise step in the entire process. As the glass cascades down like a shimmering waterfall, laser sensors continuously scan each tiny fragment to detect its color and composition. The moment brown glass, green glass, or even a stray ceramic shard is identified, the system instantly fires a precise puff of air, shooting it into a separate stream. The speed is almost unbelievable. Tens of thousands of pieces are processed every single minute. This guarantees that the cullet is sorted with perfect accuracy by color, because even the slightest mix of the wrong shade would ruin the quality of the recycled glass. Thus, the sorted cullet continues moving along the conveyor belt, directed into separate storage areas where it piles up into massive stockpiles, calmly waiting to be transformed into brand new glass bottles. 70% is the maximum proportion of the batch that can be comprised of cullet, or recycled crushed glass, waiting to be transformed. This recycled material cannot enter the furnace alone after sorting and grinding, as it requires a precise blend of raw ingredients to stabilize the melt. The recipe begins with pure silica sand, which serves as the primary element bestowing clarity upon the future glass. Engineers then introduce soda ash or sodium carbonate to significantly lower the melting temperature and conserve energy throughout the entire firing cycle. Limestone is added to the composition to strengthen the final structure and ensure stability once the form hardens. In specific formulas, manufacturers also mix in dolomite, alumina, or various metal oxides to strictly adjust the color and physical properties. Why is the inclusion of cullet considered the most critical part of this industrial recipe? To the untrained eye, it might seem that fresh raw materials would yield a purer product, but without cullet, the mixture would require excessive heat, whereas this recycled component allows the melt to flow faster and cuts energy use by up to 40%. Consequently, adding just 10% more cullet to the batch reduces total energy consumption by about 3% and significantly lowers carbon dioxide emissions. Once the formulas are determined by the factories, the mixture is blended until perfectly even and prepared for the thermal processing stage. The mix is then fed into a massive gas furnace, where the temperature rises to about 1,750 degrees Celsius, which is hotter than molten lava erupting from a volcano. One can notice how the granular mixture gradually turns into a dense, glowing liquid under the intense heat. But this is just the beginning of the transformation. Workers inside the facility must wear specialized fireproof suits and heavy protective gloves to survive the environment. The surrounding heat, reaching nearly 3,000 degrees, is almost unbearable for the human body without protection. Once the ingredients stabilize, the mouth of each crucible is hermetically sealed to maintain these extreme thermal conditions and control the melting process. At first glance, melting seems like a rapid phase of liquefaction, but in reality, it requires 24 hours for the sand to turn into a substance that flows thick like lava. The brilliant glow at the bottom of the furnace reveals liquid glass, a dense, shining mass that has finally reached the perfect temperature and viscosity. For the next 5 hours, the glass remains in this molten state to allow any remaining gases to escape, ensuring the highest purity in the final material. Therefore, to give this liquid mass a specific form, a mold is required, making mold creation the next pivotal step. Engineers employ advanced computer-aided design software to draft the mold with high precision, controlling every line, dimension, and thickness to meet rigorous technical standards. From this digital blueprint, molds are manufactured using cast iron or alloy steel, materials capable of withstanding temperatures of up to about 1,400 degrees. These forms are then prepared to receive the molten glass and shape it from the inside out. Once the molds are fully completed, they are carefully installed into the double blow production line, which remains one of the most reliable methods for shaping hollow products like soft drink bottles and food jars. The forming process initiates by dropping distinct lumps of molten glass, known as gobs, into the initial blank mold. These gobs are severed from a continuous stream of liquid glass, reaching temperatures of around 1,011 degrees Celsius, possessing the perfect viscosity for consistent shaping. Inside the preliminary mold, a powerful jet of compressed air is blown in from above, pushing the hot glass outward against the metal walls. This action forms the initial shape known as a parison, which resembles a hollow, bubble-like structure with a narrow neck. Still glowing with intense thermal energy, the glass is gently transferred to the final mold, located just a few inches away on the same production line. It gets more complex further on. Here, a second burst of compressed air is shot directly into the center of the parison, stretching the softened glass outward until it presses tightly against every contour of the mold's inner cavity. In just a matter of seconds, the full shape of the bottle takes form. It seems like a simple mechanical repetition, but in reality, every valve and sensor is synchronized down to 1,000th of a second. This extreme level of control enables the manufacturing of hundreds of thousands of bottles per day, each nearly identical and flawless. One can notice how the glass bottles, just released from the oven, radiate a deep red heat, their surfaces shimmering in the dark like glowing metal rods. Dark mechanical arms then move in with seamless programmed precision, gliding effortlessly into place to retrieve the ware. Each bottle is lifted with care and set down onto the moving conveyor belt. The whole scene unfolds in calm silence, perfectly synchronized without a hint of haste. The conveyor belt slowly guides the newly formed bottles, their bases still glowing with residual heat, toward the cooling area. They travel through a long yellow tunnel where the temperature lowers little by little, giving the glass time to settle safely without cracking from thermal shock. This careful annealing stage takes its time. It may last several minutes, and sometimes even stretches to tens of minutes before the material is fully stabilized. As the process moves forward, the cooled glass bottles reach the inspection stage. Here, an array of optical sensors and high-speed cameras examines each unit in real time. Every detail is checked, and the moment a defect appears, whether it is a crack, a bubble, a scratch, or a tiny warp, the system immediately flags it and pulls the bottle off the line. Transitioning to the next level of quality control, the system focuses on a close examination of the bottle's mouth. Each bottle is rotated with precision by an automated mechanism, while optical sensors and mechanical probes team up to detect flaws, such as a chipped edge or the smallest deviation in dimension. Only bottles that pass this strict check are allowed to move forward to the packaging zone. After clearing all inspections, the glass bottles are carried to the palletizing section, where robotic systems take charge. Designed for accuracy and uniformity, these machines organize thousands of bottles with ease. It is visible how a clamp mechanism with suction cups lowers, grips a full row of bottles, and sets it carefully onto the pallet layer. To protect against impact during handling and shipping, a protective sheet is placed between each layer. When the stack is finished, an automated wrapper secures the pallet in film and tags it with a code corresponding to its production batch. Finally, the glass pallets are moved into storage, neatly stacked and waiting for transport. From here, the bottles travel across the globe, ready to be filled and serve their purpose in daily life. High-pressure hot water and steam blast into the bottles to strictly eliminate any dust or bacteria. Why is such intense thermal treatment required for apparently clean glass? To the naked eye, the containers look ready for use immediately upon arrival. However, this rigorous cleaning stage is mandatory before the world's most iconic soda touches the glass. The process is only gaining momentum. One can notice how the clean bottles move down a high-speed conveyor to the filling station. Automated nozzles descend to fill each one with Coca-Cola, measuring the volume down to the exact milliliter. Simultaneously, carbon dioxide gas is injected to lock in that signature fizz. Precision machines at the capping station press crown caps onto the rims immediately after filling. High-precision sensors integrated into the line conduct a detailed inspection for tightness. At first glance, capping seems like a basic mechanical step, but in reality, it ensures every bottle is perfectly sealed against leaks. And this is not the limit of the quality control measures. A high-speed camera system scans the glass for cracks, overfilling, or misapplied labels. It is visible how the Coca-Cola bottles continue gliding smoothly along the conveyor belt, lined up in perfect formation like a programmed assembly. They move through this stage with a steady, precise rhythm toward the water spray station. A high-pressure jet of cold water hits the neck of each bottle to finalize the exterior cleaning. Therefore, the perfectly sealed bottles are packed into cartons and loaded onto pallets for distribution. The stock moves into cold storage, ready for the global supply chain. The product is shipped to millions of stores worldwide, from small roadside shops to luxury hotels. The beverage waits for the customer in its finished form. Hundreds of newly formed bottles gleam under the inspection lights as the production cycle concludes. The transformation from jagged, dirty shards to pristine containers is physically complete. This process returns value to what was once considered waste. At first glance, the result seems simple, but in reality, it proves the efficiency of modern thermal recycling. The conveyor belt carries the batch toward the final packing station. Why is this closed-loop system critical for industrial sustainability? The aesthetic appeal of the glass is obvious to the eye. It serves as a physical confirmation that technology can bypass the need for raw resource extraction, preserving the environment through engineering. One can notice how the automated systems handle the fragile items with gentle precision. The glass is now chemically identical to virgin material, ready for immediate use. But this is just a pause in the loop. The material retains the potential for infinite future processing without loss of quality. The product leaves the factory, fully restored and prepared for distribution.